Last episode, you built a neural network from scratch. Forward pass, backprop, PyTorch loop. Today, activation functions. The one choice most beginners skip, and it silently breaks their network. Hi, I am Mahaz. Deep Learning Series, Episode 2. Sigmoid, Tanh, ReLU, Leaky ReLU ELU, GELU. By the end, you will know exactly which one to use and why. Why do activation functions exist at all? Without them, every layer is just a linear transformation. Stack 100 linear layers, and you still have one linear function. Depth buys you nothing. Activation functions introduce nonlinearity. That is what lets a deep network approximate any function. Curves, boundaries, interactions that no straight line can capture. The activation function is applied element-wise after the weighted sum. It is the only part of the neuron that is not a straight multiplication. Sigmoid, the original. Formula, 1 divided by 1 plus e to the power of negative x. Output is always between 0 and 1. Looks like a smooth S-curve. Perfect for probabilities, which is why it is still the right choice for binary classification output layers. The problem, the gradient. Look at the tails of the curve. As x gets large in either direction, the curve flattens out. The gradient approaches 0. When you multiply near-zero gradients across many layers during backprop, the signal vanishes before it reaches the early layers. Those layers stop learning. This is the vanishing gradient problem. Rule: do not use sigmoid in hidden layers. Use it only in the output layer for binary classification. Tanh, hyperbolic tangent. Output range, -1 to 1. It is zero-centered. That matters because when activations are centered around 0, gradients in the next layer are more balanced, positive and negative, so weight updates do not all push in the same direction. Tanh is strictly better than sigmoid for hidden layers, but it still saturates at the extremes. Large positive or negative inputs still produce near-zero gradients. The vanishing gradient problem is smaller with Tanh, but not gone. In deep networks, it still hurts. Rule: Tanh is a decent choice for shallow networks. For deep networks, move to ReLU. ReLU, rectified linear unit. The modern default for hidden layers. Formula: output equals the maximum of 0 and x. If input is negative, output is 0. If positive, output equals the input. That is the entire function. Why it works: for positive inputs, the gradient is always exactly 1. No matter how deep the network, that gradient does not shrink. Vanishing gradient problem, solved for positive activations. Why it is fast: no exponential computation. Just a comparison and a clip. Networks with ReLU train faster than sigmoid or Tanh networks. PyTorch, torch.relu of x. Or pass in.relu as a layer in your sequential model. ReLU's one flaw: the dying neuron problem. If a neuron receives a large negative input, its output is 0. Gradient is also 0. No signal passes through. The weight update for that neuron is 0. If this happens consistently, because the weights push the pre-activation permanently negative, the neuron never activates again. It is dead. It contributes nothing to the network for the rest of training. In large networks, up to 10 or 20% of neurons can die. The network keeps working but with less capacity than you think you have. Cause: a learning rate that is too high, or poor weight initialization, pushing neurons into the permanently negative zone. 2 fixes for the dying neuron: Leaky ReLU and ELU. Leaky ReLU. Instead of 0 for negative inputs, use a small slope, typically 0.01 times x. The gradient is never exactly 0. Dead neurons cannot happen. The slope is a hyperparameter called alpha. You can also learn it. That variant is called parametric ReLU or PReLU. ELU, exponential linear unit. For negative inputs, it uses an exponential curve that smoothly approaches minus alpha instead of cutting off at 0. Outputs are closer to 0 mean, which helps gradient flow. ELU is slightly more expensive to compute than Leaky ReLU because of the exponential. In practice, Leaky ReLU is the more common fix. Use ELU when you want smoother negative side behavior. PyTorch, nn.leakyReLU with the negative slope argument. nn.elu with the alpha argument. GELU, Gaussian error linear unit. What BERT, GPT, and most modern transformers use. Formula x times the cumulative distribution function of the standard normal distribution evaluated at x. In practice, approximately x times sigmoid of 1.702 times x. What it does differently, it gates the input probabilistically. Instead of hard-cutting negative values to 0 like ReLU, it smoothly weights them down based on how probable they are under a Gaussian distribution. The result? A smooth, non-monotonic curve. Unlike ReLU, GELU can have negative output for small positive inputs near 0. This gives the network more expressive nuance. When to use GELU, any transformer-based architecture, BERT fine-tuning, GPT-style models. For standard MLPs and CNNs, ReLU or Leaky ReLU is usually fine. PyTorch, nn.gelu as a layer, or f.gelu from torch to nn.functional. Decision flowchart. One question at a time. Is this the output layer? Yes. Use Sigmoid for binary classification, softmax for multi-class, no activation for regression. Is this a hidden layer in a transformer or attention model? Yes. Use GELU. Is dying neuron a problem? Are you seeing many dead units or slow convergence? Yes. Switch to Leaky ReLU. Otherwise, start with ReLU. It is fast, it works, and it is the default for a reason. One practical tip: if your network is not converging, try switching ReLU to Leaky ReLU before touching the learning rate. Dead neurons are a surprisingly common silent culprit. PyTorch reference. Every activation in one place. Torch.ReLU of x, or nn.ReLU as a layer. No arguments needed. Torch.Sigmoid of x, or nn.Sigmoid. Remember, output layer only for binary classification. Torch.Tanh of x, or nn.Tanh. Shallow networks, or RNNs. nn.Leaky ReLU with negative underscore slope equals 0.01. Fixes dying neurons. nn.ELU with alpha equals 1.0. Smooth negative side. nn.GELU. Transformers and attention models. Recap. 6 activation functions. 1 rule each. Sigmoid, output 0 to 1. Binary classification, output only. Vanishes and hidden layers. Tanh, 0-centered, -1 to 1. Better than sigmoid in hidden layers. Still vanishes deep. ReLU, the default hidden layer activation. Fast. Gradient of 1 for positive inputs. Watch for dying neurons. Leaky ReLU. ReLU with a small slope for negatives. Dead neurons eliminated. Easy swap in. ELU. Smooth exponential negative side. Slightly slower. Use when you need near zero mean activations. GELU. Smooth probabilistic gating. Default in transformers. Use it for attention-based architectures. Challenge. Swap ReLU for GELU in your EP111 network. Plot both training loss curves. Does GELU converge faster? Post the result. The activation function is not decoration. It is the nonlinearity that makes depth useful. Choose it wrong, and your network either saturates, dies, or fails to fit anything a linear model could not. Next episode, loss functions. MSE, binary cross-entropy, categorical cross-entropy, what they actually optimize, and when each one lies to you. Subscribe. Loss functions episode drops very soon. Drop your ReLU versus GELU comparison in the comments. See you in episode 3.